whenever you're ready.
Okay, so yeah, welcome to this session of memory management. So we have our first paper by series, an in-memory database for large-scale monitoring system. The speaker is Yongluan Zhou. Actually, Yongluan Zhou is oh, no audio on my end. So can you hear me?
Yes, we can hear you.
Okay, so I think that is okay. Okay, so let me repeat. Yongluan is actually a professor in DIKU of University of Copenhagen, and he actually leading the data management system lab. He has served as the head of the MSc in computer science, and he actually is alumni of NUS, so where I'm now in. So I will give now I will give the mic to Yongluan. You asked me to turn the page, okay?
Yeah, thank you. Thank you for the introduction. So I'm presenting our work on Pi series. It's a joint work with a lot of colleagues, so I'm not going to name all the co-authors. The Pi series is a in-memory time series database for large-scale monitoring systems. So on the right-hand side of this screen, the first picture shows the overall architecture of ByteDance's monitoring system, as well as the position of Pi series in the data processing pipeline of ByteDance. So the Pi series usually used for designed for short-term storage and processing of time series data. Typically in ByteDance, it's the latest 2 hours of data. So in this paper, we did an analysis of ByteDance's production workload. So we found out that in ByteDance's production workloads, there are tens of billions of dimensions of time series data. So by a dimension of time series data, we meant that the data with a unique time series key. So each dimension has a unique time series key. A time series key, you can look at the table in the middle of this page. A time series key is composed by the metric name, like memory usage, CPU usage, and a list of text in the form of key value pairs, like which describe the data, like the location and the operating system, etc. In ByteDance's production workload, we can also observe that there are many new dimensions being generated per day, and this growth rate is increasing over the years. And we also see that the metadata occupies a very significant part of the memory consumption. So in the workload we collected, it's more than 80%, which actually suggests that we have to do an efficient compression of the metadata. So the metadata mainly composed of the time series key that I just mentioned. We also observed that the queries involved in the data processing workload in ByteDance often involve multiple dimensions of data. So which means that we have to access multiple dimensions and quickly retrieve the data and so on. So this actually suggests that we have to develop a system that efficiently index the metadata, basically the time series key of the time series data. So we have to do all this in the scale of tens of billions of dimensions and with a very fast growing number of dimensions. Next page, please. So based on these observations, we developed Pi series, which is an in-memory database. That's the prominent feature of our system is that it efficiently indexes and compresses the metadata of high-dimensional time series data. So the memory layout in bi-series is composed by an active buffer and a static buffer. The active buffer is designed for high throughput ingestion, which doesn't do any data compression. And static buffer is designed to achieve high efficient data compression. So both the metadata and data points are compressed. We did not develop new algorithms to compress the data points. Our contributions mainly on the metadata compression. So we use a trie-data structure to achieve both indexing, efficient indexing, also efficient compression. We also develop a data conversion scheduler to determine when and how we move the data or convert the data from between different data structures of the two buffers. So we did experiments, actually a series of experiments using both a benchmark and the ByteDance production workload. We showed that bi-series can achieve low memory usage and low query latency in comparing to existing time series databases in both the benchmark and the production workload. That's all for my presentation. I'll be happy to answer any questions.
Okay, thank you. So let me check. If you have any question, you can put on the chat or Q&A. So let me now go to Fura to see what other question we have. Okay, so let me take a look. So this one, okay. I think, okay, the first question is, what is the overhead of decomposing data and does it impact query latency? So, yeah. So Xuanhua has put an answer there. Okay, maybe I'll read this first, and then Yongluan, if you have any comments, you can actually answer this question further. The overhead, the answer from Xuanhua is actually the overhead from the data points and metadata. From our evaluation result, the query latency will double from around 20 US to 15 US when the dimension is less than 1 million. When the number of dimensions grow larger than 1 million, the overhead will be decreased. I mean, the ratio will be decreased. So, Yongluan, do you have anything to add?
So just to clarify, right? So our system did both compression on the data points and the metadata compression. So for the metadata compression, of course, there is some overhead, but on the other hand, the metadata compression, the data structures storing the compressed metadata is also used for indexing. So it's somehow also improved the query latency by doing more efficient lookup of the dimension that should be involved in the query, right? Involved in the answering of the query. So in that sense, it also speed up the query. And yes, at the same time, it has some overhead. Of course, you have to look through the trie, right? It's not like a hash index or something. Yeah.
Okay. Okay, there is another question there. I mean, are we going too fast? Okay, so we have a few. Okay, I think the second question is, in the slides on memory usage or ingestion throughput comparison, Garena had a high ingestion rate. It was mentioned that the reason was that it does not compress data. But its memory usage is not high in comparison to other systems in spite of this. Any insight into this would be helpful. Okay, this is the question. Let me see. Okay, again, Xuanhua has put in one answer. Garena has a good compression performance on data points, but not about the metadata. When the dimension grows, the tech TV will grow. The memory consumption from metadata will be larger than the memory consumption of data points. That's what bi-series tries to target. Okay, so I think The main thing here is we are actually trying to reduce the memory consumption and also the compression of the metadata. So, Yonglan, do you have anything to add?
Yeah, just maybe I mentioned it maybe in the video that I didn't clarify enough, right? I meant Gorilla doesn't do metadata compression. I don't mean that metadata data point compression, right? So Gorilla does do data point compression. So that's why it's
correct.
still low data memory consumption, but still we do metadata compression, so we can achieve like half of the memory consumption of Gorilla. Yeah, if you
I have to say, in terms of data points, Gorilla has done a very good job because we actually also looking into how to compress data series, time series data. So we find that Gorilla has really done a fairly good job on compress the data. But
yeah,
of course, not like what we are doing by series doing here is more on metadata as well as data points.
Yeah, we actually adopt the same algorithm as Gorilla because it's we find it also very efficient and very effective too, right? So
right.
Yeah.
Okay. We have one more question. So do you see by series customized for specific operators, or it can support a wide range of query types? I think Yonglan, you have to answer. There's no reply here. No one help us.
yeah, sure. So so by series now doesn't support the other operators other than lookup of the time series keys. So the time series keys are so the queries are after passing the query. So the system does is to retrieve all the data that's involved in the time series key, and also based on the time range, and and retrieve the data. And all these other operators are actually processed by the query server. As you see in the first page of the slides, the architecture, the queries are processed there. So by series only support the selections filtering based on the time series key and the time range. Yeah, that's.
So let me see whether there are other questions in the chat. Oh, there's one. Is it? Oh no, it's actually it's another issue. So I'm one of the authors, so maybe I shouldn't ask questions. So but anyway, so we actually have one thing I want to highlight to the audience here. So we actually, as you see, we have millions of dimensions. So this is really interesting, actually motivated by one of the applications in ByteDance. This is actually one of the application here is actually monitor the pair-to-pair communication between different machines. So they actually want to have the networking performance in very accurate. You can think about it's a network profile. It's basically machine-to-machine performance, network performance in terms of latency, bandwidth, and so on and so on. So this is very important because within ByteDance, there are a lot of services actually rely on very high throughput and low latency. So that's why they ByteDance have invest a lot of budget in terms of hardware and software. So if you can see this, that's why the time series here we handle is quite high dimensional, because you can think about the pairwise. Basically, it's unsquared. And if we increase the number of machine, then even further is unsquared speed of increment. So I think that is why we have so big dimension. Of course, there are other applications. I just give you one example.
Yeah, exactly. So one more issue is that this high dimension is also due to many short-term tasks. Every time you have a short-term task, you create a unique series key. And also every time you allocate like a container, right? You start a new container, then you have a new ID, a new description of the time series. So all these dynamic dynamic deployments. It's one.
Okay, so I think we time is up. Thanks, Yongluan. Okay, thank you.
Yeah.
So we have the second speaker here, Kyrgos. Is it Kyrgos Kapis? Hello. Hello. Hi. Nice to meet you here. Okay, let me share my screen. Okay, so now I give the stage to you. Hello, we cannot hear you. Hello.
Yoro, you need to unmute.
You have mute. You need to unmute yourself. Do you ask to unmute? Okay. Okay,
Do you hear me
great.
now? So,
Yes.
hello from Greece. I'm Yoros Kapes, and I will highlight some key points of our work. So, can you move to the next slide, please?
Okay, sure. Oh, sorry. Okay.
Thanks. So, software containers are widely used to run data-intensive applications in multi-tenant hosts. Containers achieve efficiency by executing the applications directly on the host operating system. So, as a result, the containers of different tenants share the same host kernel. The host kernel allocates resources to containers, manages resource usage, and enforces isolation. It also provides system services to containers like I/O handling, memory management, and networking. However, the sharing of the host operating system kernel across containers of different tenants can be problematic for 5 reasons. First, the sharing of the kernel leads to unfair use of resources, as tenants compete for shared kernel services like the page cache. Second, the shared kernel enforces a global configuration of system parameters, complicating their customization per tenant. Third, it introduces software overheads like kernel locking. Fourth, the development and adoption of new file systems specialized for containers is a slow process. And finally, the shared kernel opens up a large attack surface for attacks or bugs. We can overcome these limitations by running file systems completely at user level, but this introduces its own challenges. A user-level file system should be accessible by multiple processes and correctly handle state consistency across concurrent operations. The file system should also provide per-tenant configuration flexibility, and its interface should preserve the POSIX semantics. So you can advance on the next slide, please. So in this work, our main idea is to provision separate file systems and IPC path per tenant and serve them at user level with reserved resources. We introduce a Polytropon toolkit as a collection of user-level components that can be used to build configurable user-level file systems for containers. The Polytropon toolkit is very flexible and allows to build different types of user-level file systems with custom settings tailored to the container workload requirements. We introduce the container pool abstraction, which groups and isolates the containers of each tenant per host. Our toolkit offers a file system library that is linked with container applications and allows them to access file system services at user level. The file system service component provisions the file systems of a pool using composable lib services. So each lib service provides a user-level storage functionality like a local file system, a remote file system, a cache, or a union. Polytropon routes the I/O requests to the file system services through a dual interface. The default path of the dual interface passes both the control and data operations at user level, where the legacy path passes both through the kernel. The user-level IPC component is highly optimized to support efficient communication between applications and the file system service. For fast request communication, we introduce a relaxed concurrent queue blocking, or RCQB, that relaxes operations ordering and allows the parallel completion of queue and the queue operations. For fast data communication, we introduce a shared memory optimized, or SMO, pipelined memory copy. So our experimental results indicate that Polytropon provides scalable and stable storage performance while serving data-intensive containers. In comparison with storage solutions based on kernel modules, Polytropon achieves up to 14 times lower latency while serving 32 tenants with RocksDB over network storage. Additionally, Polytropon reduces the time span for source code processing up to 2.9 times. Our results also highlight the high performance of user-level path of Polytropon. For instance, RCQB achieves up to 52 times higher performance than other state-of-the-art queues, and SMO achieve up to 66% higher data transfer throughput. So this concludes my lightning talk. I'm happy to take questions. Thank you.
Thank you. So let me see the questions. Let me check out the question on. Okay, let me refresh. Okay. Okay, now there's one question in the Hurrah. Interesting work. Is there a reason why you focus on using Ceph as the underlying storage? Would you expect similar result if HDFS or clusters is used instead? This is asked for Brian. Yeah.
Thanks for the question. We believe that other distributed file systems like HDFS or clusterFS can be used with Polytropon, given that they provide a user-level client which can be transferred to a lib service, and they can benefit from the provided isolation. In this work, we used Ceph as underlying storage system because it provides a library-based client, which it was easy to transform to a lib service. The second reason that we used Ceph was that Ceph provides a kernel-based and fuse-based client, in addition to the library-based client, which helped us in the evaluation process as we were able to compare Polytropon with both a fuse-based and a kernel-based solution.
So is there any other question? Let me check the Q&A. Check. We don't have here. Okay. Let me refresh one. Okay, so I think I do have some question for you. It's quite interesting work. So yeah, so I have. Let me start with experiments. You mentioned that actually you have 52 times speed up on the let me see, RCQB, right? So this is really impressive. Can you explain a bit more on this?
So we compared our queue RCQB with other queues, especially LCRQ and wait-free queue, and we achieved 52 times higher performance than other queues in high parallelism. So our queue splits operations in two parts. The first part allocates NTQers on queue slots, and the second part executes these operations. So our queue is better on workload that is parallel.
Okay. Okay. The other one is, okay, so actually it's quite, this user level is quite, the design is very good for performance. And I think there are a lot of flexibility also, but actually one question is on the safety and the failure handling. So how do you address them?
You mean how
I mean,
we address?
For example, security, because once you have user level, then of course, then you have faster. Yes, but, I mean, that's for sure. But what about security and access control, this kind of thing? How do you handle that?
So we use different pools per tenant on the same host, and each tenant uses its own user-level file system services. So different tenants are completely isolated each other. So we do not support cross-tenant sharing, but inter-tenant sharing is supported, and we believe that a tenant there is no problem for a tenant to run a shared file system service for its containers.
But is there anything they may you know I know you put we need to try to protect each other's data, right? So I think how do you guarantee this kind of access control in the user level?
About the storage of the data.
I'm talking about how to, for example, you have multiple talent, right? So you need to guarantee that one talent cannot access the other talent's data, right?
Yeah, but in this work, each tenant has its own file systems. So each tenant has completely separate file system instance from other tenants.
I see.
If two tenants want to collaborate, then they must join a shared pool.
I see. Okay.
And then a solution that that provides multi-tenant sharing will be needed to provide access control, multi-tenant access control.
Okay. In that case, if we run your file system in I think, yeah, now I realize the question asking. So if we want to deploy in HDFS, that becomes a yeah. So in this case, so I think it would be very interesting if you can work on extend your idea on HDFS and so on.
Yes. Are you talking that a tenant can use HDFS as a backend storage?
Yes. Yes.
Yes, I believe that a tenant can use HDFS because HDFS provides user-level library client, which can we easily transform it to a lib service and use it in Polytropon.
Okay. Do you have anything to add? I think, let me final check whether there's question there. Okay. So we don't have other question on Hua and the chat. So do you have anything to ask? Okay.
So I'm
no,
fine.
Okay, thanks. Thanks for joining us.
Thank you very much.
Okay. So we're running slightly earlier, but it's fine. Let's move on. Okay, thanks.
Bye. Thank you very much.
On. Okay. Let me share the screen. Okay. So the other paper we have BA overlay. So the speaker will be Yu Sun. So she is a third-year PhD student from sunny Binghamton University. So her research area is OS and cloud computing. So I will give the stage to you. I will make it full screen. Okay.
Well, thanks for the introduction. And my name is Yu Sun. I'm a PhD student at SUNY Binghamton. Today, I'm going to talk about our project on how to improve the performance and the efficiency of container file systems. The title is A Block Accessible Overlay File System for Fast and Efficient Container Storage. Containers are widely used today. An overlay file system is crucial in containers to mount a layered container image and thus present a unified file system view to applications running inside a container instance. However, overlay approach will increase the I/O path and impose non-trivial I/O latency. In some write operations, the cost is very large. For example, if we are going to write a file 1 in the lower layer for the first time, a costly copy and write will be involved. We need to copy file 1 from the read-only lower layer to the writable upper layer first, then doing write operations in the copy of the file in the upper layer. Copy and write mechanism results in the write latency, especially in large files. Even to write a tiny portion of a file will copy up the whole file, which will negatively impact the performance. To this end, we propose a new file system, BA overlay, which is a lightweight, block-accessible file system. It has 3 features: block accessibility, copy after write, and the highly compact file format, bcopy and write. First, BA overlay writes in block granularity rather than file granularity. Second, BA overlay uses the copy after write mechanism, which changes the sequence of copy and write, do the copy from the lower layer asynchronously. As we can see in this figure, when we write the orange dash part of file 3, we write the map portion of the orange dash part in the upper layer directly. Then we conduct the slow and the asynchronous read later, which reads the orange part 1 from the lower layer asynchronously. This division allows BA overlay to hide the latency of the read operation from the applications, which only wait for the completion of the write, so the writing is very fast. Last, BA overlay provides a new file format, bcopy and write, for compactly storing overlay files to save storage space. So let's see the next slide. For example, we can see in the figure that here we measured the first write latency using a state-of-the-art overlay file system. One is AUFS, the other is overlay 2. And in addition, we include the BTRFS and the ZFS, which are copy and write featured file systems, compare them with BA overlay. The x-axis shows the file size, and we change the file size from 1 kilobyte to 4 megabytes. Y-axis shows the completion time. It measures how long one write completes. When the file size increases to 4 megabytes, the completion time increases to 11,944 microseconds under the traditional overlay 2 file system. While on our solution BA overlay, the completion time is constant at around 170 microseconds. So our evaluation demonstrates that BA overlay successfully improves the I/O performance of both micro benchmarks and real-world applications. Also, it can save the storage space compared to the traditional overlay 2 file systems. Thanks for listening.
Okay. Anyone want to ask question? Maybe you can unmute. Now I'm actually looking for who are. Any question here? Okay, let me take a look. Oh, we do have some question in Hua. So the first question, hi, so why don't we just put the database on the separate location, or we use some volumes? You know, we don't use overlay to store database.
I think that's a good question. Yes, definitely we can do it in that way to store the database in the separate location, and it will not involve the copy up. But by doing that, we will lose the benefit provided by the container image, which is portability and flexibility. And also, it will bring the overhead that to distinguish whether the data should be stored in a container image or it should be stored in volumes. And third, though people are advised to use volumes, but in the practical setting, we still put the data in the container images. As reported in the large-scale analysis of the Data Hub dataset. Over the analysis of 500,000 public container images, there are around 37 are read-only object code and libraries, and there are about 44% of the document files, such as Microsoft Office files and texts, the source code, and many of which are supposed to be modified. So I think the OLE file system is still important in the practical setting, because usually people are still store the data in the container images nowadays.
Mm-hmm. So you mean in your, because just now you list a lot of numbers, I cannot remember all. So maybe you want to elaborate more. So in what kind of application that actually your overlay design is good at?
Actually we test in our evaluation that we test the some real world applications like YCSB on MongoDB and suspension on Bicycle. In all of these databases, our BA overlay performs much better than the traditional overlay to file system. So I think like in these databases, the container image is still important to store the data.
So just curious, so how is the performance compared with like just now we have user level file system proposed by Kyrgos and also maybe other file system. I'm just curious.
Yes, in the 20 minutes presentation recorded video, and there are some revelations of them, and I think one of the evaluation demonstrates that BA overlay is 100% better than the traditional overlay to file system. So I think it's very large.
Okay. Let's move on. Oh, we have one question here, Q&A. Oh yeah, so we have one before. Okay, we have one question in Q&A. So as you can see, Maru asked, how does BA overlay perform if app is doing writes with ODirect? Basically, if application using the mode ODirect, the writes in ODirect, so how do you handle this?
Actually, it's block 0, I think. Can you say the question again?
Can you see the question? Actually, it's in Q&A. So basically, how your system handle if the app is using the ODirect? Do you know? In write file system, you can use ODirect, right?
We don't.
With the mode ODirect.
We don't specifically handle the ODirect.
Maru, do you want to clarify? If you want to open your mic. Hello?
Yeah, let me check.
No, I mean Maru is I mean asking the audience. Seems she's not responding. Okay, so never mind.
You can talk now.
Yeah. Okay, great.
No, it's not. I'm just saying that I allowed them to talk, but they have to unmute themselves.
Oh, yeah. I suppose we can talk, right? So, but okay, okay. I need to ask to unmute.
Are you there?
Yeah, I think he's there. So how can I do?
So I
Ask,
ask to unmute.
ask to unmute. Yeah, we have some time. We have another question in the Hua, so I think we can be more interactive. But I don't know how to. I don't have to write to even. Oh, I can promote it to panelist. Okay.
But only them. Yeah, no, you cannot unmute them. They have to do it. You can
Okay.
over-
Okay. So. Yeah. Oh, where's he? Okay. So Maru, can you unmute if you want to ask the follow-up this question? Okay, let me, okay, take time. Let me move on. We can come back to this question later. Okay, let's move to another question in Hua. So, asked by Tianyi, okay. So interesting work when breaking down a file into block granularity, how does your system handle situation where block mapping shift? Okay, so example, when a block 0 in read-only becomes block 1 after update. So basically the block mapping has changed. How your system can handle this?
Yeah, that's a great question. Block 0 means the first block data of a file. For example, if the block size is 4 kilobyte, it means the first 4 kilobyte data. And our solution BA-overlay logically partitions an overlay file into a sequence of equal-sized blocks. So block 0 means the first block data of a file. For example, if the block size is so after the update, the block 0 will still be the block 0 and it won't become the block 1.
Oh, so you mean it won't become block 1? It just
Yeah.
block 0 is still block 0?
Yes.
Because you maintain the logical mapping there, is it?
Yeah, yes. I just mentioned if we set the block size as 4 kilobyte, the first 4 kilobyte will always the block 0, and the second 4 kilobyte will be the block 1.
Okay.
So they won't be changed if we do some updates to the files.
So how do you do the garbage collection? Because you do copy
we
on
don't
write.
do it. We don't do about the garbage collection, but we have some other optimized for the block granularity. Because we know that if we use block granularity rather than the file granularity, it will result in the more fragmentation problem compared to the file granularity. Yes, so we use the copy after write mechanism to write first. So because when we do the write operation, we will write to the blocks to the corresponding position of the file in the upper layer directly. So we only need to wait for the write operation. So the write is very fast. And then we do the asynchronous read later to read the remaining part of the file from the lower layer to the upper layer asynchronously. So by doing this, we will eventually copy up the whole file and without impact the performance of the write. So to mitigate the problem will be caused by the fragmentation.
Okay. Okay. Thanks for the good work. Okay. So I think we are done. Maru, do you have a last minute? You want to check your questions? You can unmute yourself. No reply. Okay. Okay, then thanks you. So we can end here. Thanks. Okay, so we have next paper. Okay, we have next paper. Okay, let me share the screen first. Okay, let me introduce the speaker. So we have Anu, right? Anu.
Anuj.
Anuj. Okay,
Yeah.
so he's a researcher in Microsoft. And okay, so I worked in Microsoft before, almost 10 years ago. Working on high performance computer system and networks. He did his PhD in CMU under Dave Anderson and Michael. So I will give the stage to you.
Okay. Hi, everyone. Thanks for coming to the talk. I'm Anuj, and this is an introduction to our paper titled Challenges and Solutions for Fast Remote Persistent Memory Access. One of the biggest recent advancements in computer hardware is that we finally have fast durable storage in the form of non-volatile main memory like Intel's opt-in persistent memory. Although we have had very fast data center networks with only a few microseconds of latency, we were stuck with slow durable storage for a long, long time. For example, even the best SSDs out there take around 10 microseconds to make a write durable. With persistent memory DIMMs, the latency of a durable write is only around 100 nanoseconds. This is way lower than a data center network round trip, meaning that durable storage is now faster than the data center network instead of slower, which reverses a historical trend. The broad question at the center of our work is this: how should we design fast distributed systems for persistent memory? Since persistent memory performance is closer to DRAM than to SSDs, we should use the blueprint provided by the huge amount of recent work on fast distributed systems that use DRAM to hold their data. This includes many, many key value stores, many transaction processing systems, and several state machine replication systems, etc. A specific question that we address in our paper is this: what design decisions that were made by these aforementioned systems need to change if we modify them to use durable, persistent memory instead of DRAM? As one example, it is well known that if an application needs to write to remote DRAM, doing so with one-sided remote direct memory access provides lower latency than if we were to involve the remote machine CPU with a remote procedure call. However, we show in our paper that the opposite is true if the application needs to write durably to a remote machine's persistent memory. And because low latency remote writes are such a fundamental building block of numerous systems, this is one aspect of the design that likely needs to change. Could you go to the next slide, please? Compared to DRAM, we find that persistent memory has several distinct fundamental properties that pose unique challenges for networked access. We show that much of these challenges in efficient access to remote persistent memory arise from the fact that CPU architecture is not yet optimized for persistent memory. Let us take bulk remote writes as one example, and the paper contains many more. This graph shows that the peak bandwidth for bulk writes to remote persistent memory with RDMA is around 45 gigabits per second and 22 gigabits per second with RPCs. In this experiment, RDMA saturates our data center network, but if we take a deeper look on the top right, we see that there's a challenge and there's room for improvement. So here's what happens. The server's RDMA NIC injects data into the server's L3 cache at around 45 gigabits per second. Although the NIC writes to sequential cache lines numbered 1 through 3, the CPU eventually evicts these cache lines to persistent memory in a somewhat random order. This is highly inefficient because persistent memory DIMMs are optimized for sequential writes. And the randomness of this particular access pattern generated by the CPU's cache eviction technique amplifies the persistent media writes from 45 gigabits per second, which is the good put, to 85 gigabits per second. In the paper, we show how disabling an important networking optimization in CPUs called direct cache access solves this problem by forcing the NIC to bypass the cache and write directly to persistent memory. For RPCs, the bulk write bandwidth is low because CPU cores are slow at copying volatile network buffers to persistent memory. We show how the server CPU can offload these copies to a DMA engine on the CPU's die to get line rate with RPCs. Overall and put together, our paper presents a new set of techniques and pitfalls that designers of persistent memory-based distributed systems can find useful. Thank you, and I'm happy to take questions.
Okay, thanks, Anuj. Okay, let me see questions. Oh, by the way, so in fact, even after the presentation, you can still interact with the audience in Hua, the app. Okay, I still saw some question come up after the presentation. Okay, so specific to the talk for this. Okay, we have one question here. Okay, so a question on P-write. How to guarantee the ordering between RDMA write and read? I think he mentioned one flag, IBV send fence flag, or leaks processes writes and reads in order when they target at the same address.
Yes, so I assume this question is for the RDMA write and RDMA read that we have in this primitive called the P-write. For those two operations, the ordering is guaranteed because we issue both those operations on the same NIC queue pair or the same NIC connection. And operations within the same queue have ordering dependency, especially the read after write dependency. So those two are ordered, yeah.
Okay. Do we have other questions? Okay. Do we have a question on Q&A? No. Okay, so I do have when you see you have tried to you mentioned the flash or L3 cache will actually cause random writes to
yep.
to PRAM. So I was wondering, so because if you say your solution is to disable, to bypass the cache, right?
Yep.
So I'm just wondering, so in general, of course, if you talk about streaming application, like the packet comes in, maybe it's true, but what about for application with some kind of locality, but it's random access to, for example, as some kind of random write to have a scatter, and then what will happen? Because the cache will have some locality is good, right? So if you bypass the cache, that means you actually lose the locality.
Yeah, so you do lose some sort of performance by foregoing the direct cache optimization. And I think you're right that if the workload was random writes to the remote CPU's cache or virtual memory, then the trade-off might look different than what we showed, because in our case, the application's good put was benefiting from the fact that it's sequential writes, which were turning into random writes into persistent memory. But if the application was originally generating random writes, then it's not clear which approach is better. Like, should we let them go directly to persistent memory, or is it okay if we stage them in L3 cache? So yeah, that's an interesting workload that we didn't explore. But the code which we are going to make as open source, it contains the scaffolding and the scripts, for example, to disable DCA and experiment with this. So it should be pretty straightforward.
Yeah, so the other thing I find we actually also have some ongoing research on this PRAM. So we find the NUMA. Hello, anyone want to ask questions? Okay, let me finish my question then. So I find the NUMA is the architecture of current DRAM, and also the PRAM can be one issue though, because I think the QPR link have very limited bandwidth right now.
Yes.
So I don't know whether you have other good solution for that, or what kind of architecture are you looking for maybe in the future?
We didn't look at that problem, and we made our lives simpler by not considering that problem. And I totally agree with you that that's one of the very important problems. For example, in data centers, we have the NIC attached to only one CPU because it's not affordable to have like 2 NICs per machine. And then if that CPU socket wants to write to the persistent memory on a different socket, which is totally reasonable, then what are the performance characteristics? And I'm sure they're very complicated, and reasoning about them is very tricky. And I think that's like one of the messages that we are trying to put forth in this paper, that like just like we understand for now performance of CPU caches and DRAM and our DMA, we need to build a similar understanding for performance of persistent memory. One thing I would like to add is that there is a recent paper called SoCC. It was a tech report on arXiv. Now it's a paper in OSDI 20, I think. In their paper, they use DMA engine on the CPU in a different way than we use a DMA engine. So we use a DMA engine on the CPU to accelerate copies from volatile network buffers to persistent memory buffers. But their tech report version, they use the DMA engine to improve the performance of cross-NUMA persistent memory copies. They found that like doing it with a CPU core was slow for some reason. I don't understand the exact hardware architectural concepts, and I would like to, but that's one reference that will be very useful for this question.
Let me check it out. I think that's very interesting. Yeah. So let me see whether there's another question, just in case there are other questions there. Oh yeah. So you see, actually they have a question coming out. Okay. The second one is from your experience, how disruptive do you find the combination of RDMA plus NVRAM for existing systems? Yeah, so it's a $1 million question.
Yes, so I think that there are 2 aspects to disruptive here. One is like, will big companies and big cloud providers adopt persistent memory? That I don't know the answer to. But if we just look at the research systems that have been published, so my own papers on HERD and FAST and other great work like FARM, Dr. TM, all of these papers were targeting systems that do require some sort of persistence. Usually, for example, when we think of OLTP system, transaction processing systems, people think of durability and
yes,
as one of the guarantees. And all of these systems were being designed with persistent memory as an explicit or implicit assumption that, oh, we make this design for DRAM, and we hope that it will work well for persistent memory when it becomes available in the future, because these systems were being built around 2015, 2016, when we had some hope that persistent memory would become real, but it became real in 2018. So I think for these systems, it is disruptive in some ways. I think most of the design of these systems can remain the same. And even if you were to use the same design, it would work fairly well. But I do believe that there is a fair amount of work to be done to re-examine the network protocol, the use of RDMA versus RPCs. And there was this whole line of work on like whether we should use RDMA or RPCs, and I was involved in it. And I think that needs to be rethought in the light of persistent memory. So I would say it's fairly disruptive. But the other thing is that persistent memory, in my experience, was surprisingly fast. I was personally very surprised that with the random access write rate, the random access read rate, the write bandwidth that these devices could support. So I think the optimistic view, or actually a positive view, is that all of these works did the right thing, or the designs that they made, they will work very well on persistent memory. But of course, there are some knobs and techniques that we provide that you can do to further improve performance by a fair bit.
Mm. Yeah. Mm-hmm. Mm-hmm. So do you think we I mean, because in old story, I mean, we read some articles quite some years ago, we predict that PRAM will eventually replace DRAM and so on. But actually now it's not, because PRAM is still slower than DRAM, right? So, and then I think to my own opinion, so how disruptive it is, it depends on, in the end of the day, is how is the performance cost ratio.
Exactly.
Yeah, so is actually if I think the PRAM can offer like 10 times performance price ratio, then I think that will really a big game changer on that.
Yeah, I totally agree that that's one. The other is just like marketing factors that are outside everyone's control. One other thing that I like to think about is that unlike DRAM, persistent memory doesn't clear itself once you reboot the system. So
yes.
that's also tricky because
yes.
How are you going to clear out 3 terabytes of persistence or 6 terabytes of persistent memory on a reboot if you're just treating it as DRAM?
I mean, good or bad. I mean, they're always good or bad, right? It's long run tower, and then you have good or bad because you have, there's a lot of issues, interesting issue there. So
Exactly.
Okay, so I think we need to go to the next speaker. Okay, so thanks and Anuji.
Yeah, thanks everyone.
Thanks. Okay, now Chandra. So we actually try to share the screen. Okay, wait a minute. Okay. Okay, so let me introduce the speaker. So Chandra is a final year PhD candidate. So are you on the job market? Okay, so final year candidate, a PhD candidate in UC Santa Cruz. His research interests include the application of machine learning and other AI techniques to optimize the performance of storage system. So yeah, so he is actually looking for a job. Good. He's expected to graduate in March 21. So good. So now I think everyone pay attention. Someone is on the market, job market. Okay. So now I will give the stage to Chandra. Okay.
Can you hello? Yeah.
Yeah.
Hello everyone. My name is Chandranil Chakraborty. Thank you. So I'll go again. Hello everyone. My name is Chandranil Chakraborty, and this is the lightning talk on improving the accuracy, adaptability, and interpretability of SSD failure prediction models. I am from University of California, Santa Cruz, and I'm advised by Professor Heiner Litz, who is also the co-author in this paper. Can you move to the next slide, please? For this project, we analyzed telemetry data from over 30,000 SSDs from Google's data centers spanning 6 years. Now, predicting SSD failures is an inherently challenging problem due to the problem of class imbalance. SSDs fail rarely, and hence the number of data points from healthy drives far outnumber the number of data points from failed drives. For our data set, out of the 30,000 drives we examined, only 4,000 failed at some point. A fraction of the failed drives were replaced and were repaired and put back into production. The delay in repairing the drive lasted up to a year, resulting in even fewer samples from the failed drives. As a result, the dataset contained over 40 million data points from the healthy drives, while only 15,000 data points for the failed drives, which is identified by inliers on the diagram on the right. So here in the diagram, we obtain a PCA of all the features, reduce it to 3 dimensions, and you can see the inliers and the outliers. The inliers is the healthy drives, and outliers, the failed drives, are difficult to distinguish. Now, compared to prior work, we first provide a comprehensive machine learning comprehensive analysis of machine learning techniques to predict SSD failures with highest recall and accuracy for both minority and majority classes. We optimize our approach by addressing the challenges of imbalanced data sets and feature explosion. Secondly, we show how one-class models can be used to predict unseen failure types not seen during training in a dynamic data center environment. And third, we propose one-class encoder, autoencoder, an approach to interpret the predictions of the model to enable understanding of all the most important reasons for failures. The key idea for our work is to train the models on the majority class while ignoring the minority class. It prevents the model from overfitting to a set of known failure drives and improves the generalizability of the models, and as it can detect unseen failures not seen during training. Additionally, we introduce feature selection for improving the most selecting the most important features contributing to failures for our work, and perform extensive hyperparameter tuning to find the most suitable parameters for our models. Next slide, please. Now, for our work, we introduce, as mentioned, we introduce autoencoder models that can improve accuracy by up to 13%. The figure on the right shows the improvement in terms of ROC-AOC score for the baselines that we used. And so we sweep the number for this experiment. We sweep the number of failed drive observations, including the training set, from 10% to 100%, simulating a dynamic environment where new failure types emerge over time. Note that our one-class techniques do not include any failed drives in the data set, so we plotted their performance as a straight line. From the figure on the right, we could see that our baseline's performance depends significantly on the amount of minority samples in the training set, that is the failed drives, but for our models, it is dynamic. For example, if only 50% of the failed drive observations were included in the training set, our proposed one-class autoencoder models outperforms in the random forest, which is the prior work, by 13%, and neural network and SVMs by 33%. This shows that, but in particular dynamic environments, one-class techniques are a better choice than other techniques used in prior work. Thank you so much, and I would be looking forward to your questions.
Okay, any question from the audience? Okay, let me stop sharing and then Q&A here. Okay, let me take a look at who so far. Okay, we have some question here. The first question is asked by Rodrigo. So SSD hide a lot of underlying interest cases and only export a subset of status information through through SMART. So what do you wish SSD vendors to export it to further improve your prediction? So basic question is, so besides SMART, what do you want from the vendor in order to improve your prediction?
Yes, I think the reason why our prediction models were a bit better because the features that were utilized, we had in total 21 different features, which was the drive characteristics, as pointed out, like collected by SMART. There was also error flags, error counts, status flags. So in our experience, different error counts are a good metric. It's a good metric. Different error counts, like correctable error, was in our data set was one of the top distinguishing features. There was also cumulative bad block count. So these are the features, some of the features, at least for the Google data set, contributed to the errors, and eventually failures. So errors, different types of errors, and is a good metric how we can determine failure. But having said that, I think there are other parameters also that we should look at. Like, so for some of my work, I was told that some firmware inserts were crashing the SSD, and that is like purely specific to certain vendor for certain case. So we have to do more analysis to see what is the exact thing that happens at the back end. Based on our work, there is a different several combination of features that contributes to failures. And we were not out to any particular ones. For example, the reasons that were determined by our autoencoder models, the most popular reason, for example, for our data set was correctable error, but it was only flagged 37% of the times. So it's not ubiquitous, so it's very combination, and it's a combination of different features. One feature doesn't provide all the information that we need. So, and in short, it's a ongoing research. Right now, I would see my best answer would be error counts and status flags, but we have to do more research to find out which is better. Thank you. Thank you for the question.
Okay. So I want to follow up though. Of course, when we look at the failure, there's always external factors and internal factors. External factors like temperature or whatever. Yeah, and the internal factor is like you may have the in terms of SSD, you may have FTL and so on. So I'm just curious. So if we do like open SSD, so we suppose we even open up a lot of information of FTL to you, will it improve your prediction?
I would, I think more information won't hurt. The idea is it will just gets discarded at worst, in the worst case. So I think we can do as many features like, and then doing an unsupervised way, trying to find anomalies. And I think we can find more features, what leads to failures. The problem with this is that we need a huge data set for a long periods of time. So we need to like have a lot more data, like a lot more. The problem is obtaining failed drive information. So because SSDs fail rarely, so we have problems in obtaining data about the failed drives. So that is the challenging part of the problem of this work.
I would say this is also a privilege though, because not many people have access to the real data. So we actually are struggling. So for example, if we want to do something, actually we're struggling to have very few data or very little data.
Yes. Yeah. Data is a privilege nowadays. Yeah, and I think some of the sponsors that we have here, if they can open up some of their data sets, I think we can get more data and try to find more features contributing to failures, which is often I think it's of good significance in if you can predict with some more certainty than what we have right now.
Okay. So and then shall we move to the next question?
Yes, definitely.
Okay, so Ziyang asked one question, because I think because your model trains on only healthy drive, if it possible that we combine information on the failed drive to improve the accuracy further?
So this was the prior work which trained on both classes. So which was our baseline. So based on our experiments is that because the failed drive, the number of data instances is very small, it kind of, if we train on the minority data, it kind of overfits to those set of known failure types. And the one which is, say, not belonging to the failed representation based on incomplete representation, it tends to flag them as healthy drives. So the way that I think our work was slightly better was because we trained only on the healthy drives, which is cheap to find. We can find a lot of them and try to find as close a tight representation of what a healthy drive can look like. And anything which doesn't conform to this, we flag them as failure. And we look into the reasons. I think this, in our case, adding minority sample data kind of confuses the model a little bit, or makes it overfit to small set of data. So I think only made for this problem, majority class training only on the majority class makes more sense.
Okay, so do you want to comment that actually if now your study is on SSD, if we want to extend the study to hard drive, for example, so I mean, how can you apply your methodology or finding to hard drive?
We would have to look at some of the features that we looked at. If we can find that in hard drives, there've been certain number of work in hard drives which has been successful to an extent. And I think if we get similar sort of data, whether it's because the technology is different, but the data that we're collecting, it's kind of the same. If we can find similar sort of data, then I'm confident that we can use readily the same models for hard drive anomalies finding.
Yeah,
anomalies.
In fact, that's why I'm curious, because many are actually under a smart interface. So I think they have quite similar. They should have quite similar lock. So I'm looking forward to that. If you want to do the study, it's quite interesting. Okay.
Yes, and I'm willing to do it. I'm very happy to do it. I just need some access to more data. So anyone can find my email,
get back to this.
Yeah. Give me any data. I would try to do and analyze and try to do stuff for you. Give you some what contributes to failures and would extend my knowledge as well. So that would be good.
Okay, any other question from the audience? Okay, let me see, last check on Hua, just in case they have more questions. I think we don't have. So I think we are sharp. Okay, so we are right at time. Okay, thanks everyone. Thanks all the speakers here. And also thanks audience. I think the session is done. So I think I will give it back to the Christina.
Thank you, Bingchen. Bye.
Yeah, change it. Nice to meet
Thank
you.
you, everyone. So we have another gather break now, so feel free to go and interact with the presenters or the other attendees. And then we'll be back here at 2:30 with a very interesting panel on serverless compute. Thanks.
Okay, see you then. Bye.